Due to the safety concerns of workers cleaning the exterior walls of high-rise buildings with atypical shapes, various types of exterior cleaning robots have been studied. Among them, we present a rope-on-rope system consisting of a dual ascension robot, DAR, that moves by winding a rope in a robot called Rope Riding Mobile Anchor, RMA, that improves the maneuverability of the DAR by connecting the rope ends of the robot. The DAR is an under-actuated system, which the number of actuators is fewer than the actual degrees of freedom of the system. As a result, it can control X-Y axis motion, but cannot control rotational motion. Therefore, DAR experience residual vibration after movement and cannot directly control it due to the lack of degrees of freedom. And as the number of ropes increases, as in the current system, the amount of vibration will intensify. The purpose of this study is to analyze the rope-on-rope system and reduce the residual vibration represented by the rotation of the DAR. To control this residual vibration, we first performed a kinematic analysis and dynamic analysis of the ROR system. During the dynamic analysis, the ropes are assumed to be a simple spring damper model, and the tension on each rope is calculated. We define the position coordinates of each robot affected by this tension and the rotation angle of the DAR. Given the uncertainties and disturbances increased by the nature of the rope-on-rope system, we decided to experimentally obtain the exact parameter values for the dynamics equations. As the input of the experiment, we entered the chirping input of x acceleration from 0 to 2 Hz. Then we used the data of phi, the result of the experiment, to get the transfer function of the ROR system. The following presents RVCA, a control algorithm that reduces the residual vibration of the ROR system. It utilizes input shaping as a feed-forward control for the movement of the DAR and feedback control using PD control for the stationary state. A disturbance observer is applied to improve the overall control performance. Input shaping is the most common control technique for controlling residual vibration in mechanical systems. It is a feed-forward control technique that changes the amplitude and timing of the system input by analyzing the natural frequency and damping ratio of the system. After obtaining the natural frequency and damping ratio from the transfer function obtained earlier, we shaped the x acceleration of the DAR and generated a trajectory accordingly. PD control is applied to maintain stability when external factors such as wind or external obstacles cause vibration. It can also be utilized to compensate and reduce the residual vibration of DAR that cannot be completely reduced by input shaping. There are disturbances to the control methods described previously. These include length variations due to the assumption of a spring damper model for the rope and slippage issues in the drive that winds the rope. We designed and applied a disturbance observer to represent these disturbances that interfere with the control input. Further experiments allowed us to define a nominal plant using the transfer functions of the ROR system. The Q filter was applied in the form of a first-order low-pass filter for fast response and minimization of resonances. We constructed a test bench implementing the ROR system with a simplified DAR for the experiments. Rotary and magnetic encoders were used to calculate and adjust the position of the DAR. When the DAR is moving, the RMA is stationary. Therefore, in this experiment, the RMA was assumed to be a mass of 1 kilogram fixed to the rope. Acceleration trajectories with PD control, input shaping, RVCA, and an open loop were generated for the following experiments with the same average velocity. The DAR is moved 0.8 meters horizontally along the position trajectories derived from this acceleration trajectory, and phi, which means residual vibration, is measured. These are the experiments for each condition. We compared the experimental results with the results of a simulation of the system model, which had been obtained earlier under the same conditions. The graph shows maximum amplitude and settling time of the residual vibrations generated by the DAR for each experiment. Simulation values are represented by red and black bars, while experimental results and their averages are represented by blue lines and squares. As the simulations are based on the model, its reliability can be verified by the fact that the simulation results are within the range of the experimental results. The table depicts the average maximum amplitude and settling time of the experiments with its reduction rate compared to open loop. As the table shows, RVCA is the most effective with the highest reduction rate. The performance of each controller was also evaluated using the root mean square error, RMSE, calculated from the experimental results. Similarly, the RVCA is the most effective with the lowest RMSE. This approach enhanced the overall performance of the ROR system and provided a robust foundation for future advancements in precise and reliable control systems.